All right, just started the recording. So topic 30 is on ensemble methods, and I'm actually going to break this up into two study groups. So it'll be today and tomorrow. Today we're going to talk about bagging methods, which is a subset of ensemble methods, and then tomorrow we're going to talk about boosting. So today and tomorrow, this week will just be topic 30. I do want to point out that the presentation for this project is happening sooner than usual. So if we take a look at our calendar over here, let me zoom in. We are on week 6, and usually we do our presentation on week 1 of the next phase, but we're hitting 30 this week. We have 31 on Tuesday, followed by an office hour next Wednesday, one more office hour, and then our presentation will actually be on the Wednesday of week 8. Reason for that being that hopefully by then you all will have at least some modeling done, and I will of course talk about it during the one-on-ones to make sure that that is on track. So we'll do our presentations that day because we get straight into phase 4 stuff. There's very little break between, there's no break between phase 3 and phase 4. And yeah, take note that the presentations for phase 3, if you're doing it on that day, doesn't have to be your final model. And during the office hours, I'll talk more about what it could look like if you're not at your final model yet. So I just want to take note of that sooner than usual presentation. Questions about this? Okay. All right. So to talk about ensemble methods, the term ensemble methods, first and foremost, is an umbrella term. And it's an umbrella term for any sort of model that makes use of other models in conjunction with each other. And there are many different ways that you can go about it. One of the main methods is bagging. And then another main method we'll talk about tomorrow is boosting, as I've talked about. So by default, all ensemble methods default classifier, and you'll see what I mean by that, is actually a decision tree. So all of these ensemble methods are built upon decision trees, but depending on the ensemble method and how specific we're talking, it can be different models as well. That'll make more sense, I think, after tomorrow. But first, let's review some trees. This is the structure of a regression tree. Our classification tree would be the same, just that the output or the terminal nodes will be classifications instead of specific values. Now, remember, we are splitting at each level into 2 parts based on some partition that the gradient descent process has deemed to be the best. So for our regression trees, it is usually by mean squared errors. As you can see, the mean squared error of the node, the splits are already where it is best split to have the lowest mean squared error on either side. And then for classification, it would be to reduce entropy or Gini inequality as much as possible. So quick overview, remember that we're just splitting at every node into 2 branches. Cool. So next, to talk about classification trees, exactly the same. You're splitting on some sort of condition, true, false, to reduce entropy as much as possible. Basically the purity of a leaf. All right, so when we're visualizing classification decision trees, if we take a look at, I'll put all, okay, these are all images. If we think about decision boundaries, and in this case, this quick example is an example with 4 different outcomes, 4 different classes based on their colors. Now, depending on what your max depth is, you'll get different decision boundaries. So for example, this is depth equal to 1, meaning that you just split once. So even though we have 4 classes here, we only have 2 outcomes. If we do depth equal to 2, we're splitting one more time over here. This will be our decision boundary. Anything that falls within this green area, even this yellow, this purple, this yellow over here, will be classified to be green. Anything over here will be classified to be blue, anything here will be yellow. So as we increase the depth, because every existing partition will be partitioned once more, the number of sections we get increases exponentially. So as you see by depth equal to 4, you can see that we have not four partitions, but we can have up to, I think, is it 8 or 16? I forget. Up to 2, 4, 8, up to 16 different partitions in this space. And this is depth equal to 4. Now, the problem with depth and why in the labs, the main hyperparameter that we're tuning is max depth. Why depth is important is it can lead to overfitting. And that was one of our biggest cons when it comes to decision trees that we talked about almost 2 weeks ago now. But yeah, one of the biggest cons when it comes to decision trees is the problem of overfitting. So as you can see here, with this same example that we had before, with this decision tree regressor, we have two different models being built. So here we have the blue line that is max depth equal to 2. And the green line is max depth equal to 5. And as you can see, if it was max depth equal to 2, our tree would have ended right around here. But max depth equal to 5, you're building way more leaves. As you can see here, based on the actual regression, this is actually very similar to what the residual plot for a tree regressor would look like. You can see here with the max depth of 2, yes, it's fitting some like average values, but at a max depth equal to 5, you can see that there's some overfitting occurring. Like these points over here look to be outliers, but are still being fitted to with this decision tree. So max depth is something that we will tune for any tree-based model, but as you can see, least overfitting. And this is only increasing depth from 2 to 5 because it does increase exponentially. Any questions on our recap with trees so far? All right, so trees are great. And as a quick review, some of the advantages and disadvantages. First, works well with nonlinear relationships. As you can see here, yes, there is some overfitting, but this still fits better than just a straight line across. It's very easy to interpret. You're just looking at your splits and your different conditions. Feature selection is done for you because if a feature is not important, it's never going to be split on that feature. And it also accounts for interaction for you. Now, disadvantages, I think the main disadvantage with decision tree is its tendency to overfit, especially if they're completely pure. So very likely these outliers over here were when we allowed the leaves to become completely pure. Your model that you've trained is accounting for those outlier points there. So very, very overfitted. Also instability. Due to the overfitting, small changes in the input data can cause large changes to the structure of the tree. Cool. So what can we do about this overfitting problem? As we can see, a decision tree by itself, very, very sensitive, can overfit very easily, which sometimes is a good thing if you really want to fit a model specifically to your training data. But let's try and combat this overfitting. So cue ensemble models. And the whole idea of where the conceptualization of ensemble models came up is through the whole idea of wisdom of the crowd. So this came from this one story that I guess a mathematician started or a statistician noticed that, you know, those games where you try and guess like how many jelly beans in a jar or how heavy is this ox? I think in like 1906, the example is how heavy is this ox? When 800 people guess how much it weighed, the actual weight had only a 1% error from the median guess. So the idea here is using one expert learner, you might get better results if you were just to aggregate a bunch of weak learners' guesses, if that makes sense. So idea here is, let's say you had like, I don't know, a very seasoned farmer who knows like the weight of oxen, I guess. They would not have as good a guess as taking the median or mean of a bunch of people's guesses. And that's kind of where the idea of ensemble methods came about. So takeaway here is that we can learn a lot by combining many different learners called an ensemble method. So in essence, we can combine the output of models that are not accurate enough on their own to aggregate their guesses together and get through some sort of mechanism, get an aggregated prediction. So this is where the term forests come along. And I think last week we had a preview of random forest, which is basically a lot of trees together. We're going to talk about that later today. But yeah, anything that uses multiple models together and aggregates their information is an ensemble method. So today we're going to talk about two named ensemble methods. We're actually going to talk about random forest. That's the one later. But right after this, we're going to talk about a model called bagged trees. Both of them make use of decision trees. All right, so questions before I get into these new models? All right. So, okay, recipe for a bagged tree. So to construct a bagged tree estimator, first what we need to do is we need to bootstrap this entire data set. And we'll talk about bootstrapping next. Next, we're going to use this bootstrap data set to build a tree. And then what we're going to do is we're going to bootstrap our data set over and over again. And each time we bootstrap our data, we'll see in a little bit what bootstrapping entails. After running a bunch of different decision trees on different versions of our data set, we then aggregate all the trees together and then output the prediction through each tree. So imagine what we can do is we can build 100 trees on 100 different variations of our data set. For regression, take the average of the 100 predictions. And for classification, take the majority predicted value. So let's say you build 100 trees on slightly different versions of the data set. Let's say 60 of the trees vote in a binary classification problem, vote class 0. 40% of the trees vote class 1. We will just say that based on this bagged tree model, the predicted value is 0 because more have voted 0 instead of 1. So that's the whole idea of bagging. So bagging, we'll talk about that later. Let's talk about bootstrapping first. So what is bootstrapping? Bootstrapping is the method to sort of introduce a little bit of randomization into our modeling process such that overfitting doesn't really occur. So because trees are prone to overfitting, they have a high variance, very sensitive to changes in the data set. This is especially true if the trees are built to full purity in each of the leaves, very connected with max depth, also can be kind of connected to the min sample split, if you remember that hyperparameter. But a way that we can prevent this overfitting is to take bootstrap samples with replacement from our training data that is the same size as our training data. So in this example, this is our original data set. We have 9 data points in our original sample. And to create each bootstrap sample, we're going to sample with replacement. So because we're sampling with replacement, you can end up with these slightly different looking data sets. So here you can see that there are only 2 yellow points, but you can end up with 3 in some samples. For the orange over here, even though it appears twice, some samples only have 1 orange data point. So you're basically sampling with replacement to create a bootstrap data set. So for every tree in a bagged tree classifier, you're going to take a different bootstrap sample from your data set, and it's going to have the same size as our original training data. Another example, you can see that this is our original data set. We have 4 rows of data. If we bootstrap the data set, you can see that this one bootstrap data set is going to take row 2, row 1, and then row 4 twice because we're sampling with replacement completely random. Each row has the same probability of being drawn at every draw, I guess. Questions on bootstrapping? All right. So first step is bootstrapping. Next is aggregating. So the aggregating component comes in after we take each bootstrap sample. We're going to fit a decision tree to each sample. And remember, each decision tree is going to have a low bias, high variance, very, very prone to overfitting. So you're going to repeat this process for however many trees you want in your model. And then, as I mentioned that from before, just aggregate that result. So if you have 100 trees, see which one is being predicted most out of the 100 times. And then for regression, just take the average of those trees. Questions about this while I look up the documentation for bagged trees. Bagged tree classifier cycle.
Yeah. I had a quick question for the previous slide.
Yeah.
So is it basically like it's a randomized? I know you said it's a randomized. It's randomized, so there's no overfitting. So you're just randomizing the combination of.
So we're randomizing the rows, and every time we're sampling with replacement, meaning that to create this data set, rows can be repeated, and some rows might not even be represented at all. So they're just going to randomly pick, say, let's say I have numbers 1 through 10. If I want to bootstrap 1 through 10, you can sort of imagine, okay, I'm going to roll a 10-sided dice 10 times and then take those corresponding rows. So let's say 6 comes up like 4 times. That will be for the first 4 rows of your bootstrap data set. And then you roll like a 1, 2, 3. So it'll be 6, 6, 6, 6, 1, 2, 3, and then another 3, number 7, 8, 9. That's an example of a bootstrap data set too.
Okay. All right. Thank you.
You're welcome. Anything else?
Another question. How would this be affected if you're also like adding I forgot what the terminology is for when you have like too much of one data and not enough of another one, where you add,
Smote.
yes.
Okay.
So how is this affected by that? Like, wouldn't it lead to like even more random or even like inaccurate results?
So if you're not using Smote at all, because of the sampling with replacement, overall, on average, your class balance will still remain this roughly the same on average across all of your different bootstrap samples. Introducing Smote, you actually introduce Smote before the modeling process, and this bootstrapping is done within the modeling process itself. So let's say you do Smote and you create like 1,000 synthetic data points. Those 1,000 synthetic data points will also be used in the bootstrap. If that makes sense. How it affects the model, the bootstrapping with Smote kind of occur independently. I'll go more into Smote next week during an office hour. But yeah, I think they're pretty independent. They shouldn't have too much effect on each other.
Okay, thank you.
You're welcome. Anything else? Okay, so I do want to show you all here that this is the bagging classifier that you can import from scikit-learn. And then you can see here we have base estimator. Now this is what I said that like by default, it fits a decision tree. So see how the base estimator is just a decision tree classifier. You can actually build a bagging classifier and any other classifier. Typically best on trees because each tree will overfit to its bootstrap sample. But there is a case where you can fit like a naive Bayes bagging classifier, do you like, or even like a K-nearest neighbors bagging classifier. But results tend to be best if you bag a decision tree. In your projects, you don't have to bag different things. You can definitely just use the default. And then as you can see here, other parameters that are new for Ensemble methods, number of estimators. So the default here, you're gonna build 10 trees and do like 10 different bootstrap samples. This would be something that you could tune as well. And yeah, these are the main things here. And then here you can actually say whether you want to bootstrap it or not. If you're using a tree, if you're using a decision tree, if you don't bootstrap, every tree will end up being the same. But yeah, these are the main new hyperparameters. Something that's also neat, you can actually as the base estimator, use decision tree classifiers with different decision tree hyperparameters. So you can actually nest these models if you'd like. But typically you don't have to do that. All right. Questions about this?
So is this best used for multi-classification models? So specifically, if you have like huge data sets and it's going to be multiple, lots of features,
so
lots of rows.
like
the
so
Chicago data set as an example.
Gotcha. I would say for number of outcomes is not affected. In terms of number of outcomes, it doesn't matter. In terms of the size of your data, I would say that any ensemble method, the bigger the data, it'll take much longer to run because you're training so many different classifiers all at once. Is there an advantage to using this for larger data sets? Possibly, yeah, it is possible. So let's just say that in that car crashes data set, if you decide to do that one, let's just say you have a feature that is that tends to cause your trees to overfit a lot. So let's say wet weather tends to really help determine the severity of an accident, as an example. And that always tends to be like the first split, no matter what your tree is. Doing something like this, any sort of ensemble method, any sort of bagging ensemble method might help to reduce that overfitting to that one feature. And because you have so many different features to choose from, it makes sense to do that. But just note that, yeah, any ensemble method, because you're doing models upon models, is going to take a lot longer overall.
Got it. Thank you.
You're welcome. Amir, I saw you come off mute.
I'll wait until like you were done.
All right. How about you, Mo?
Yeah, when you said the default is 10,
Mm-hmm.
and would that result to overfitting if you don't set the. I don't know if
s-
that's your
yeah,
question.
so the more estimators for bagging classifiers, I would say the more estimators you have, the more variations in your data set your trees will see. So that does tend to lead to less overfitting, yes.
Oh, okay.
Mhm.
All right. Thank you.
You're welcome. All right, so in terms of aggregating your result, basically, let's just say that in random forest, which is the next model we're going to talk about, works kind of simply. There's just one difference that we're going to see. But basically, a bunch of different trees you have. And let's just say that you have 3 trees. One of them votes class A, 2 vote class B, majority voting, you get your final classification. And then typically your decision boundary when you're using any sort of ensemble method tends to be smoother overall. All right, so bagging just comes from, and I should have put this slide at the start, but bagging is just a combination of bootstrapping and aggregating. That's where you get the term bagging from. So if you take a look over here, this is a regular decision tree output, and this is decision trees with bagging. You can see that it does smooth out that tendency to overfit, which is very cool. Nice. I think there's one more thing before we get into random forest, which is out of bag error. So as you remember, whenever you're building any model, there's always some sort of like cross-validation process that you have to do, some sort of train test split that you have to take care of. So built into the modeling, when you use any sort of ensemble method from scikit-learn, there's what's called out of bag error that's done for you automatically. So basically for each tree within your train set, they're gonna only take 2/3 of the data to build your tree on. And then right when it's done building that one tree, it'll test with the 1/3. And that is just called an out of bag error. Just because imagine if you're building 50 trees in your bagging classifier and you want to do like cross validation on all of them, it's going to take it's going to take a lot of computational power and time as well. So therefore, they're just going to take 2/3, build your model in that, test it on 1/3, which is why you should see over here out of bag error. You can see your out of bag score there. Usually you don't have to check this because everything is aggregated anyways, but if you start to see some sort of weird overfitting patterns, you might want to look at that. But very, very rarely you do. But that's more in terms of the mechanics of how scikit-learn gets your trees to train. So you don't have to go in and validate that each tree is performing well or performing as it should. All right. Yeah, it's basically a form of cross-validation. It's just doing a train test split within each tree, which you can then verify at the very, very end with your regular 80-20 train test split on your test set. If that was a lot, then doesn't matter. Okay, so some issues with bagging, which actually kind of alludes to what I was just explained to Mo about with the overfitting. So the issue with bagging is that each one of these trees might end up still being very correlated with each other because there might be a feature that's just so powerful in generating a separation between different categories that therefore still results in trees that are correlated to each other. So I think I was talking to Sam about the car crashes example. Let's just say wet weather always leads to more severe accidents. Even with bootstrap samples, it might be that you still have that kind of correlation between your trees. You still might have the first split of your tree always being wet weather, dry weather. So you know how in trees, a lot of things are determined by the first few splits. That does often kind of tell your, or it kind of determines where your tree and how your tree builds. So because of that, sometimes bootstrapping is not enough. That leads us to our next thing, which is a random forest. Many questions at this point so far. Cool. So mechanically, random forests work very, very similarly to bag trees as we just saw. The only difference is this second step over here. So build a tree using only a random subset of the features at each node from the Bootstrap dataset. So we're going to talk through all that later, but the other steps are pretty much the same. You're going to bootstrap the data set as well for each tree. here we're just going to take a random subset of each features at each node. We're going to go through that in a little bit more detail in a bit. Then again, you're just going to do a bunch of these trees and then aggregate the trees same way as we did for bag trees. Random forest is basically bag trees with an additional element of randomness, because there is already some randomness introduced in bootstrapping, but now additional level of randomness on the features axis, which we'll take a look at in a little bit. Okay, so here for a random forest, you're gonna have to choose some number, and we'll see the default. Actually, let me pull that up real quick right now. Random forest classifier. All right, so in a random forest, you'll see that there is a feature called max features. So basically, at every opportunity there is to split, you'll only consider a fraction of your features. So let's just say you have 100 columns, you're only going to pick out a random subset of those columns to decide on your split, which is an additional level of randomness. So in that case of rainy weather always determining the severity of an accident, in some trees, the weather might not be considered at that very first split in a bunch of the trees. And by default, I believe it is the square root of the number of features. So what that means is if you have 100 features, at each split is only going to consider 10, which is much fewer than 100. It's literally, it is the square root. So that's the element of randomness that is introduced. So as an example over here, if you want to predict heart disease at this first node, maybe it will only look at blood circulation and blocked arteries, and it will only look for best splits in those two features. The other two features, it will completely ignore for that specific split. Now, note that is for the specific split. So that means over here, it's going to look at good blood circulation and arteries, but over here for this split, it might look at two completely different features as well. It's completely by random too. So here, this additional element of randomness allows it to even less opportunity to overfit. Questions about this new element of randomness that we've just introduced?
Makes sense.
Right.
Like they're essentially just saying we're going to pick random amount of features to find out like if something has a strong correlation. 6 out of 10 times, there should be enough randomness where we separate that out to see if that actually matters.
Yep, that's right.
Okay. Okay.
That's right. Yeah,
What-
and oh yes, Amir.
So my question is, it's the same features in every decision tree though, right? It's not like a randomly chosen every time it makes another leaf.
Yeah, so
Okay.
your entire data set with 100 features, but at each split, you're considering a different 10, but throughout the entire tree, each one of the 100 can be an equally good candidate for those random 10s.
Okay.
Yeah, cool. So let's take a look at some example results. So random forests, as we just talked about, decorrelate each of the decision trees by ensuring that only M features are considered for a given split. And why it's square root of the number of features that you have, why it goes from like 4 to 2 or 100 to 10, is just demonstrated to be better. So as you can see over here, the out of bag error rate, which is basically the 1/3 that that wasn't trained, the 1/3 that the tree wasn't trained on. You can see over here for max features equal to none, the error rate hovers around 9%, but anything less than that, by just using a random subset of the features, it goes down to like 6 to 7%. This orange one is by using the log of the number of features. And this blue one is by using the square root. So that means on average, basically the difference in the number of splits will not even consider a given strong predictor. And as we increase the number of trees, it will not lead to overfitting, meaning that we should make as many trees as possible until we have achieved an acceptable error rate. So if we take a look at random forests, and estimators, the number of trees that you build, the default is 100. So by default is going to build 100 trees. Now it's a little bit more, it is a little bit more efficient because at each split, it doesn't have to look at that many features, which is why you can start at 100 by default. But other than that, all of the other hyperparameters within random forest classifier are actually very similar to the ones decision tree. So max depth, the max depth of each tree, it actually defaults to let it go all pure. You have min sample split and leaf that we talked about. Max features, this is the one that tells it, okay, at every split, how many features to consider. And yeah, the rest all the same. You can even tell it to not bootstrap, but usually you do. So on and so forth. The rest are very much the same. Cool. Questions about anything so far?
Can you have
Oh, mhm.
for the graph? Can you have more than 3, or is that sort of the appropriate, like?
Oh, you
for-
mean this over here?
Yeah, for like square root, log 2, and 1.
Oh,
Is there
so
more?
this is just to demonstrate that setting max features not equal to none is better. So you would just pick one of these to do.
Oh, okay.
Yeah, and then, oh, I didn't explain, but this over here is increasing the number of trees in your random forest. So at a certain point, the overall error should start to level out. So over here, you can see that maybe after like 100 estimators, it starts to plateau off. So maybe you can stop at 100. That's what this diagram goes to show. But you typically don't need to make this diagram.
Okay, thank you.
You're welcome. All right. So again, very important to remember, because this is actually a pretty common machine learning interview question. How is the randomness introduced in a random forest? Make sure that it is at each node, not for the entire decision tree. That's a common misconception, that for each tree, you're picking like a random 10 out of 100 for the entire tree. But each tree can have all 100 features, just different 10 at every node. So that's an important one to remember. All right, so this is a blurry image. I don't know why, but in general, in terms of test error and out of bag error, random forests tend to do better than bagging, that tend to do a little bit better than decision trees. So over here, you can see that we have our the blue and the yellow lines are for random forests, which have a slightly lower error rate compared to their bagging counterparts. So this green line is the out of bag error for bagging, and the black line is the test error for bagging as well. So as you can see, pretty much for all of these trees, I would stop at maybe like 100, because all of the additional trees don't seem to help with performance very much. But yeah, that can come in your tuning. Cool. So for some quick advantages and disadvantages, advantages is actually very, very powerful. Will nearly always outperform decision trees in terms of testing error. So this is why I say you always have to check for your train error and your test error, because your decision trees might give you deceivingly high train errors, but because it's overfitted, will give you lower test errors. Again, very similar to decision trees, ability to detect nonlinear relationships, and also because of its randomness, very hard to overfit. Disadvantages is a little bit harder to interpret, because you are looking at an aggregation of like n number of trees. And also you have many hyperparameters to tune. We talked about grid search last week. You'll definitely want to use grid search. I will say that within random forest, let's say you build 5 trees in your random forest. In scikit-learn, you can actually pick out each decision tree if you want. And that library that had you output the diagram of the trees, you can actually output a GIF of all 5 or 100 trees if you want. But usually, especially for this kind of project that we're going to do for this phase, you don't have to go into that. But if you ever needed to do so for like a job or something like that, you could, which is good to know. Also, for random forests, you also have your feature importances. If you remember, for decision trees, I talked about how you can get feature importances. That's very helpful to tell you what is a strong feature for classification. You can get feature importances for any model that is built off trees. So therefore, random forest, you can definitely get feature importances. Bagging classifier, as long as you use the decision tree, which is the default, you can get feature importances as well. And what you do tend to see for feature importances is that in decision trees, sometimes it biases to a couple features out of, let's say you have 100 features in a decision tree, sometimes it might bias to like 3-4 features. But in a random forest or a bagging classifier, you'll see the importance spread out over more features. So it also goes to show that it's not overfitting and it's less, and every tree is less correlated with each other. The fact that more features are being considered. Cool. Next, hyperparameters. I kind of talked about this already, so I'm going to skip this slide. Oh yeah, and feature importances. So basically how feature importances are calculated and determined, basically by which feature reduces the criterion the most. Criterion being like the entropy or the Gini impurity. So it's basically a ratio of how helpful the feature is for classification. So this is just an example. You can get this feature importance graph for any tree-based model, as I just mentioned. Cool. So that was random forest. To kind of end off this bagging section, I also want to bring up voting classifier, which you can also use if you would like. But this, I will say, is also not in our curriculum, but it's a neat one to know. So voting classifier is a model that allows you to create custom ensemble methods by making use of, I'll show you that library in a little bit. And it's intended to be used with conceptually different models. So imagine that you have, I mean, so far we've talked about what logistic regression, naive Bayes, decision trees, k-nearest neighbors. Let's say you want to aggregate their results. Voting classifier allows you to do that. So voting classifier actually uses the same like .fit, .predict syntax. But what you do is you can feed it in a list of estimator tuples. So they have an example over here. So let's just say you have these 3 classifiers. You want to have a logistic regression, a random forest, and a naive Bayes model. When you instantiate a voting classifier, you feed it in a list of estimators over here. So this list of estimators, similar to how we did like pipelines last week, logistic regression, random forest, Gaussian naive Bayes, and then you can call voting classifier.fit.predict. So if you ever wanted to do an ensemble method with not just the same model over and over again, you could do this too, which I think is pretty cool. Just a good one to know that exists. And within the voting classifier, you can also specify majority class vote or soft vote. So majority class, same, just voting, majority wins, but also you can look at soft vote, because for some models, as I mentioned, you can actually get the probability estimates for each class. So let's say you have 5 classes, some models will give you a probability of which class it thinks it is, and it'll aggregate it based on those probabilities. So it's not as strong. It's more like a, I don't know, more like ranked choice versus straight voting. And that's something that you can tune here as well. So voting classifier is something that you can use to create your own custom bagging models if you'd like. All right, so that ends off this section. Here I have just a couple. These papers are actually the papers that kicked off random forest, and I think it was literally written in like the year 2001. So random forests are fairly, I guess, relatively new. So yeah, these are the bagging methods. This slideshow will continue. This slideshow is already on your study repo, by the way, and tomorrow we're going to continue with boosting methods, which we're going to talk through 2 other models, or actually, sorry, 3 other models that follow quite similar concepts of how they aggregate. So we'll talk about that tomorrow. But any questions on bagging that we talked about today?
I just had a question for just ensemble methods. Is it sort of the idea that it's building off like each other model, like for it's a decision tree, then it goes into bagging, then it goes into random forest? Is that the idea of ensemble, is like building off of another model?
So almost. So bagging classifier and random forest are 2 completely different models. So you would instantiate them differently. If you use both of them, they would count as 2 different models.
Okay.
Technically, you could bag a random forest, but we won't get into that. But the idea here is that you're using decision trees, is we're building a bunch of decision trees And basically, we're using an ensemble of decision trees to make our prediction. And that's where the idea of ensemble comes about, just by using a group of decision trees.
Oh, okay. All right.
Mhm.
Thank you.
You're welcome. Anything else? Sweet. All right. Well, if there are no other questions, we'll be back here tomorrow for boosting. Same slideshow. We'll just start from the middle. In the meantime, I've been seeing a bunch of your functions. Really good work. A lot of you are starting to expand on the template that I gave you all, so that's really awesome and exciting. But yeah, in terms of data sets, a bunch of people have been sending me messages about that too. So if you don't want to use one of the provided data sets, just Slack me whichever data set you're using so that I can just make sure that you're going to get okay results, and that classification would work on that data set. If you're sending me a data set, should tell me also what you intend to predict. That would be helpful to know. But yeah, as usual, send me anything you'd like based that you've done with your project. Happy to look it over prior to presentation day. All right. Any final questions before I close out for the day?
Just a quick question. Where do you want the function? 'Cause I have it done. I just didn't I just have it private. So I didn't.
All good, all good. For the function, whichever is easiest for you, to be honest, I would say you can even copy and paste it into Slack, send it to me
Okay.
that way. Mhm.
Okay.
Nice. All right. So yes, the function, I swear, will set you guys up for success with this project. It'll make your modeling process so much easier. I promise. All right. If there's nothing else, I will see you all tomorrow. Have a good night, everybody. Bye.
Good night.
Good night.
Bye.
Have a good night.